Okay, so let me continue with this fourth lecture on ability approaches to nuclear structure, and today I will come also to the advertised nuclear reactions. So yesterday I finished, I think, with this slide that somehow demonstrates the deficiencies of a calculation where we use only a square integrable basis. So this is a no-core shell model calculation for helium-6 for different basis sizes and harmonic oscillator frequencies. And this is then, this just shows the ground state energy convergence with the basis size for particular frequency. That was this one here, 16. And then I calculate helium-7. Okay, so the helium-6 is bound fine, so I could definitely extrapolate this and get something, some ground state energy, which sort of makes sense also in comparison to experiment. But then I calculate helium-7, so you add one neutron, and then, okay, the calculation also looks sort of okay, right? But then you realize that the energy of helium-7 is above the energy of the helium-6. That means that the helium-7 is unstable with respect to a decay of, to the helium-6 plus a neutron. And so now this calculation in the harmonic oscillator basis can maybe tell you like where or how much it is unbound, with some extrapolation. One can judge that, but we can say nothing about the width of this, of this ground state of helium-7. And also we cannot be sure that this extrapolation actually is reliable because this is an unbound state. So its description in terms of a square integrable basis with a Gaussian tail is not realistic. So clearly we need to do something more sophisticated if we want to look at resonances, unbound states, or even on the scattering and reaction. So for that we have to extend what we have been doing so far. So the no-core shell model or any other basis expansion with the square integrable basis like the harmonic oscillator is based on this kind of expansion. So you treat all the nucleons on the same level. You can develop some bases which depend on the Jacobi coordinates, or it depends on the single particle Slater determinants, and you expand that with some truncation, right? And all these functions that I have here, they will have some tail which will go to 0 as you increase the radius or the size. So now, however, we can use ideas from the resonating group method, which describes the nuclear system in terms of clusters. So you can imagine that your nucleus can separate into some pieces at some energy. And so now in this resonating group method, you can consider, for example, binary clusters, which can separate in some coordinate, which is the difference between the center of masses of the two clusters. And you really allow in this approach to separate these clusters all the way to infinity. So that means you can put proper boundary conditions on this type of basis expansion that could allow you to study the scattering, or if it is a bound system, then still you will get a proper tail of the wave function when the clusters are separated. So I wanted to say the following. So obviously you can also imagine that you can have another type of cluster where you will separate 3 subclusters all the way to infinity. So that is possible, and then obviously you can go on and have a part of the wave function that will allow to separate all A nucleons apart. So from this pictorial description, we can write it in a more systematic way. So again, this part would be this square integrable description of all A nucleons, like in the no-core shell model. So it depends on internal coordinates of the system, like the Jacobi coordinates, where all the nucleons are treated the same way. But then I will add another piece of the wave function, that will explicitly include clusters. And so now this will be the first cluster again in terms of some internal coordinates, and the second cluster in terms of its internal coordinates, and then some wave function of the relative motion between the two clusters. And so this coordinate will be the separation, or is the like a relative coordinate of the relative that tells us that this is the center of mass of the first cluster, center of mass of the second cluster, and this is the difference between those two. And now and then I can go on and add the cluster where I have three subclusters. And so I have an example here, is the beryllium-7. And so I encourage you actually to calculate the beryllium-7 in this exercise that we started yesterday with this code BigStick and with these interactions that I provided. So you can calculate the spectrum of beryllium-7 in the no-core shell model. So that would correspond to this part. Just to see what you get and how you can compare it to the data which I show here. But the point is that you have here some bound states, minus 1/2 minus. But then if you increase energy, you see that there is a helium-3 plus helium-4 threshold. So basically all the states up above this energy will be unbound. And for example, this state is a resonance in this helium-3 alpha. So in this picture, this would be like a no-core shell model part that calculates this beryllium-7. But then I will add this part, which will be like a helium-4 plus helium-3 that I allow to separate all the way to infinity, possibly. And that will then allow me to calculate properties of these higher-lying resonances, or even just the continuum of the two with the proper boundary conditions. But then you have another channel here. You see, if you go to 5.6 MeV of energy, you have lithium-6 plus proton. So that will be a different partition, also a binary cluster. So then you should add another piece, which will be like this will be lithium-6 and this will be a proton. But then you can imagine that at some point lithium-6 will disintegrate into alpha and deuteron. So you will have here like alpha, deuteron, and a proton. So it will be a three-body cluster. So if you want to really describe all these kind of processes that you allow even to disintegrate lithium-6 to D plus alpha, then you should also consider this type of expansion of the many-body wave function, right? And so in this expansion, as I said, these phi's would be the wave functions that we can calculate, for example, in the no-core shell model that only look at the internal degrees of freedom of the clusters. So those could be described in terms of square integrable basis. But then here I also need to include antisymmetrization of the nucleons from different clusters. So the clusters themselves will be antisymmetrized, right? But then I need also to include the antisymmetrization if I exchange nucleons from different clusters. So that's why I have here the antisymmetrizer. And then you can rewrite this with this kind of trick that you introduce an integral over the R, which is like a dummy variable, and you put here Dirac delta, and that allows you to pull this wave function of the relative motion in front of the antisymmetrizer. So this is a kind of trick that is used in this resonating group method approach. And then in this type of expansion wave function, you have an unknown variable. So let's say you compute beforehand the clusters. So that will be like known quantities once you start to build this new wave function expansion. And what you need to determine next would be these expansion coefficients. So these are discrete, but these are continuous, right? So this is sort of a schematic picture. And now in this picture I can treat these parts as basis states. yeah, that will be discrete or continuous basis function. So overall, you can see that this sort of expansion, these basis states will be non-orthogonal, obviously, and also it's overcomplete because in principle I could just stick, to one set of these. Okay, so basically, especially if I just focus on some, a range of energies, I could choose just one subset of this expansion and describe actually the complete system, the system completely. So now, if I use this kind of more general expansion, my basis will be overcomplete. But mathematically, one can deal with that, so it's not a problem. Yeah. So in general, this resonating group method started with a description using binary clusters. So that will be the simplest expansion. So you would just forget about the other parts and just look at these binary clusters. And so that's actually what we did with Sofia Quaglioni about 10 years ago. So we used these ideas of the resonating group method within the no-core shell model, and then we used the basis expansion, which would have two binary clusters. Each of them will be two clusters. Each of them will be described by a wave function calculated in the no-core shell model, and then with that we would solve the the RGM type equation to find this unknown wave function of the relative motion that I denote here as gamma. So this looks all good. One problem that appears immediately is that in this expansion, which you have to include many internal excitations of these clusters. So this nu, right, describes the quantum numbers of this system, and so in order to converge, you really have to include many of these clusters, because you can imagine, let's say you have helium-3 alpha. So if they are apart, then this description of helium-3 and alpha is good. But now when they come close together and start interact, they will exchange nucleons, and then suddenly you have to take into account many excitations, internal excitations of these, helium-3 and alpha, to really describe the correlations of all 7 nucleons. Yeah. So then this becomes prohibitively complicated to really do a good calculation in this type of expansion. So actually, in practice, what is much better is let's say, to include also this part immediately. Yeah, so that means that we will have at least 2 components of this expansion right away. So this component would be like what we do in the no-core shell model to describe all, for beryllium-7, all 7 nucleons. And then this binary cluster part that will be, for example, helium-4 plus helium-3 for the beryllium-7. And so this approach, okay, I just write it one more way, is the same thing. So I will use just these 2 pieces. So this approach we call no-core shell model with continuum, that we introduced a few years ago. And so the idea is that we have the standard description in the no-core shell model, and then we add a binary cluster, and that we treat in this expansion in the spirit of the resonating group method. And having those 2 components allows us to describe efficiently the whole system. So this component is efficient when all the nucleons are close together, while this component is efficient when the clusters are separated, right? And so it's clearly over complete basis, but we can deal with it quite well. And so now, again, so I will use this as my trial wave function, and for that, I want to solve the many nucleon Schrödinger equation. Okay, so let me just yeah, so my full wave function will have this these components. So this would be let's say the no-core shell model wave function or basis state. So that means that is an expanded in the harmonic oscillator expansion in the Jacobi coordinates or in the Slater determinants. And then I have the second part, which will be this cluster component. And let me just write it with this dummy coordinate that describes the separation of the clusters. And so then you have some part which describes the relative motion. And then I will have, so let me just call this some binary cluster state, which new are all the quantum numbers that characterize these two clusters and their coupling, and the R is again just the coordinate of the separation between the center of masses of those clusters. So explicitly, so I let's say I have the total number of nucleons is A, and then I have a subcluster which has lowercase a nucleons. So this relative coordinate is given by the center of mass of the first cluster and then the center of mass of the second cluster. Okay, so this is +1, and so this R is a dummy variable, because I introduce in this in this separation I have a Dirac delta. So this is the coordinate really depends on the nucleon coordinates, and this is just an integration variable or dummy coordinate. Okay, so this is the kind of expansion that I consider, and so now I can treat. Sorry, I forgot about the antisymmetrizer. So very important thing. So here I have the antisymmetrizer that takes care of the antisymmetrization of the nucleons from different clusters. So the total wave function must be antisymmetrized, so I have to do this. So the clusters themselves are antisymmetric, but we also have to take care of the antisymmetrization between of the nucleons from different clusters. And so now, so I use this trick with the Dirac delta to pull the antisymmetrizer, to pull this gamma in front of the antisymmetrizer. So then the antisymmetrizer acts on the single nucleon coordinates and also their spins, isospins. It doesn't act on the dummy coordinates. So and then what I can do is I can treat this and that as my basis states on which I will project my Schrödinger equation. And if I do that, then I will end up with this kind of schematic coupled channel generalized eigenvalue problem, where you have different blocks. And so the simplest block is this HNCSM, which is nothing else than just you just consider this type of basis. Okay, and so what does it mean that it's NCSM? So that means that these states are expanded in the harmonic oscillator basis. So they don't describe the system when the nucleons are very far apart. Yeah, because the wave functions will have Gaussian tail, so this only describes localized terms. So this Hamiltonian, in fact, is your standard Hamiltonian with the kinetic term and the nucleon and three-nucleon interaction, but the basis is expanded in the harmonic oscillator with harmonic oscillator basis state. So this is what we have dealt with so far in these lectures. And so now I told you that this kind of basis could be expanded in Slater determinants with a dimension of 100 million or something, right? So I don't want to have this matrix here with a block which has 100 million dimension, right? So that would not be very helpful. So what I can do now, I pre-diagonalize this. So that's what I do in the Korshell model anyway. So I will pre-diagonalize this, and then I will use the lowest eigenstates for the expansion, right? Because in general, I'm interested in the some energy range, right? I showed you this beryllium-7 spectrum, and so there I want to describe, the beryllium-7 not up to 1 GeV, but up to 10 MeV or so, right? In the low-lying regime, low energy regime. So I would diagonalize this as I would do in Korshell model, and then I will use the lowest eigenstates in this expansion. So now these states, what I have, what I consider here, would be the eigenstates of the Korshell model. So that these are not, your Slater determinant basis states. These will be already pre-diagonalized, expanded in terms of these Slater determinant basis states, right? So then the lambda would just count your, your eigenstates in the Korshell model. Obviously, they should also have J pi and T, angular momentum, parity, and isospin. So I can add those quantum numbers if I want, but for simplicity, I just write it like that. So the point is that I will pre-diagonalize, and then I will have here a delta function, right? The Kronecker delta, and obviously these eigenstates are orthonormal. So then in this block here, these are standard orthogonal states. So I have there just an identity, right? But then I have this part which is coming from, as I said, there's this resonating group method ideas, that here I have products of clusters, yeah. And so now for that I have to calculate the matrix elements, let's say, of the Hamiltonian in this type of basis. Yeah, and so to do that, I have this kind of object. I have Hamiltonian, and here I have the antisymmetrizer that acts on this state that includes two clusters, and then on the other side I have the same the Hermitian conjugate, right? So this is the kind of matrix element that I need to calculate to set up this matrix. But now these states, this A nu acting on the phi nu, those are not orthonormal. So if I just put here 1 in this, instead of the Hamiltonian, I put identity. So this is not equal to, this is not delta n nu prime delta r prime. This is not the case, right? So actually I need to calculate this, and then I include that on the right hand side as a part of the so-called norm kernel. So what I'm getting here is a generalized eigenvalue problem, right? So I have this kind of object which is called norm kernel. Yeah, so that is an additional difficulty in this business of the resonating group method, but mathematically you can easily treat this, so there is no issue. And then because I have these two types of components, one that describes the system in the square integrable basis, the harmonic oscillator basis, when all the nucleons are close together, and the other part which describes the clusters, I have to take care of the cross terms, right? So I will have a part which couples, right? That couples those two. So I will have something like this. Okay, so that these are those two blocks. So these are, we call them coupling kernels, right? But then again, if I put H to 1, then I don't get delta. So again, I have a contribution. So this is not equal to this is not 0. Okay, that's the point. So this is not 0. So I have to include it here as a coupling part of this norm kernel, right? So this, and then once I calculate all these pieces, my unknowns will be these expansion coefficients. So these are discrete coming here, and these are continuous, right, depending on this dummy coordinate r. And so now to get those, I have to solve these equations. So in general, with this scheme, what do we have to do? So first we have to calculate the building blocks, which are these eigenstates that I use in the expansion. So first I would diagonalize. I would do a no-core shell model calculation for. So let's talk about this beryllium-7. So I will calculate the beryllium-7 in the no-core shell model, and as I said, you can actually do the same with this big stick code as we discussed in our little exercise in the afternoon. So let's have beryllium-7, right? So I will do NCSM for beryllium-7. And then I will include some eigenstates. So ground state will be the 3½ minus, right? Then I will have 1½ minus is the first excited state. Then will be 7½ minus, 5½ minus, and so on. Yeah, and so you can imagine you can take, let's say, the 10 lowest eigenstates and put them into this expansion. But then to calculate your clusters. So you want to calculate helium-4. So maybe for that I can just take the ground state of helium-4, because the next excited state is at 20 MeV, while these excited states are at, this is only 400 keV, this one is about 5 MeV, this one is about 7 MeV, while the next state above the ground state of 0 plus is at 20 MeV. So maybe it's a good approximation just to take the ground state here. And
which configuration do you consider for the
Okay. So now, yeah. So if I just go back to the experimental, obviously I don't need to know the experiment to do this calculation, right? So if I just do no-core shell model and I believe that it's not crap, then I will already get something like this, and based on that I can then build my clusters. But here you can just read it off from experiment what needs to be done. So you need to include helium-3 plus alpha, because that is the lowest threshold. And then if you want to be really sophisticated, then you should also include lithium-6 plus proton. But no. So okay, so there are two bound states, 3½ minus, 1½ minus, and they are bound by 1.6 MeV or 1.5 MeV, and then the next threshold is lithium-6 plus proton at 5.6 MeV. So this is not this is a bound system. I mean, it beta decays to lithium-7, but this is a very decent system. So yeah. So again. let's say you have here the 7.5 minus state, which is a resonance in helium-3 alpha. It's below the threshold of lithium-6 proton. So in general, if you want to look at these three lowest states, you don't need really to include the lithium-6 proton. So you need this cluster if you want to look at higher resonances, and you really want to consider a decay into that channel, right? But anyway, so I now will focus only on this part where I have the helium-4 and helium-3. So obviously, in principle, we could also include lithium-6 proton, but that complicates things. So let's just now do the simple thing. And again, so I will just use 1/2 plus ground state of helium-3. So again, the excited state, or let's say breakup of helium-3, would be at I don't know, 7 MeV, about 5 MeV or so. So that the breakup of this, helium-3 will be somewhere at 6 point, I don't know, somewhere here. So if I'm interested really in low-lying energies, then this is a very good description already. And so Gabriel mentioned in his talk the helium-3 alpha gamma capture to beryllium-7. So if we want to describe that, and I will show actually example how we did that. That was the calculation that Jeremy actually was leading. So for that, this kind of basis is completely sufficient. Okay, so just to continue and to try to describe what we need to do to carry out this calculation. So as I said, so first thing is we need to calculate these eigenstates in the no-core shell model, and then we need to build these binary cluster channels from these wave functions of helium-4 and helium-3. And once we have the channels, we can calculate the kernels. So the kernels are these objects. And once we have the kernels, we can actually solve these equations. And that is done with some special technique, but actually one can use different methods how to solve this for bound states and for scattering states. So I will come to that probably tomorrow, how to really solve it, because that's a method that could be used for any scattering problem, not only for no-core shell model with continuum. So now, just to explain a little bit better this how we built these cluster basis, the cluster basis part of the wave function. So it's what I have schematically shown as this. So it's a little bit more complicated object. So let me just attempt to describe it in more details. So now I'm talking about this, what I denoted here as phi nu r. Okay, and so now this, and actually with the antisymmetrizer. So let me just put the antisymmetrizer there. So I have two clusters. So the heavier one I will just call target, and the lighter one a projectile, right? So it's just not just names. So let me just describe this one. The target will have some quantum numbers alpha and the j pi t, or in this case I call it I1 pi 1 t t1. So again, these states I will get from the no-core shell model by diagonalizing the Hamiltonian. And so this is an eigenstate, again, let's say the ground state of helium-4. Yeah, so this is an eigenstate, so I will have 0 plus 0 here, and the alpha will be, in this case, just 1. I will have a 1 state. So these are eigenstates of the no-core shell model. Then I have here, okay, so I continue on this side. So then I will have the second this what I call the projectile. Yeah, and I will couple them now with, because they have a definitive, the angular momenta and isospins. So I will couple them to something which is called the channel spin, called which I denote here as S. So we call it a channel spin. And then I have to couple. Okay, I have to include the spherical harmonics, which will describe the relative motion of the two clusters. Yeah, so that will depend on the angles of this coordinate that I have here. Right. Actually, so okay, so that's what I have on this side, and then eventually I will have there the I will have. Okay, sorry. So in this case, I have no dummy variable at this point. So here I will have the wave function of the relative motion between the clusters. So strictly speaking, this is not equal. So this is part of this full expansion. So here I would have this G, which describes the relative motion, and sorry, no, I forgot. Okay, so now I need to couple my channel spin with the orbital momentum to a total angular momentum. So I have one more bracket here, and now I couple this to J pi t. Okay, right. So I couple S with L to J with a Clebsch-Gordan coefficient, right? And then I have finally this wave function of the relative motion. That I denote G. Okay. Yeah. So that's this object here. And so now I can introduce this dummy variable R with the only purpose is to pull out the G in front of the antisymmetrizer, because now the antisymmetrizer will act on the nucleons in the target and projectile, on the wave function of this spherical harmonics, but also the G. And so I prefer, to have the G outside, because the G is something that I want to solve eventually for. So this is the unknown. So I prefer to have it like that. And so to do that, you simply introduce your Dirac delta and an integral, right? So it's trivial, but it's a useful trick. And then once we have this kind of object, what we can do, we expand the Dirac delta in the spherical part and the angles, right? Again, I hope that you are familiar with this type of equation, where you expand the delta in terms of spherical harmonics and the radial part. Yeah, and if I do that, then I integrate the angles from this. I will integrate over this, and that means that I will get rid of this dependence on the r hat, and I will introduce the r which depends on the coordinates of the nucleons. Yeah, and in the end of the day, I have this delta for the spherical part, and here I have the gamma, which depends only on the absolute value of this coordinate, of this dummy coordinate r. Yeah, so I hope that this is no magic. It's obvious, but it's useful because that allows us to have this part of the wave function outside of the antisymmetrizer. And then this is the thing that we want to find by solving these equations. Okay, and so now a few words about the Hamiltonian that we use. Okay, so maybe I could. so obviously the Hamiltonian, as before, has some kinetic term. It has the nucleon-nucleon interaction, and also can have three-nucleon interaction, right? So I can obviously include also the three-nucleon interaction, but maybe why don't we just make it simpler here? And so now these are sums which run over all the nucleons. But now what you can do is you can equivalently rewrite this in a way that you explicitly have only considered the coordinates for the first cluster and the second cluster and the part of the relative motion between the clusters, right? So I think it's more or less obvious that you can split these sums in a way that you will have, this, let's say, the internal part of the Hamiltonian for, the first A minus little a nucleons. Okay, if I put here ij, so there will be ij running up to, this A minus A. Then I will have sum over ij from A minus A plus 1 up to capital A, and that will be the internal part of the projectile. So this will be the target, this will be the projectile, and the rest you can convince yourself that the rest would be a kinetic energy that will depend on this coordinate that I denoted before as A minus AA. So that is the relative coordinate of the relative motion of the center between the central masses of the two nucleons, and then an interaction between those objects, right? Between those clusters. So it again will depend on these type of coordinates. Which it can also depend on the momenta and so on. But anyway, so let me just write it schematically like this. So this is exact, just a rearrangement of terms. So especially if you use Jacobi coordinates, this comes out very naturally. So that's what we do. So that will gives me, let's say, if I use this part, it will give me the eigenstates in this case of helium-4. This will give me the eigenstates of helium-3, right? And if I put it all together, again here, that will give me eigenstates of beryllium-7 in the nuclear shell model. And then I have these parts of, of the relative motion between the helium-4 and helium-3. So now there is a little trick that we have to be very careful how we treat the Coulomb interaction. So the Coulomb interaction obviously appears in the nucleon-nucleon interaction, right? So if I have a proton-proton part of the NN interaction here, it includes Coulomb. However, the way how we do the calculations, let's say in the nuclear shell model, we always expand with some n max, and eventually, so we never allow the nucleons fully disintegrate, right? So we never treat these interactions really. The nucleon-nucleon interaction is always calculated in some harmonic oscillator expansion and truncated. So that means that my, protons will never be allowed to separate, and I will never get in this, kind of expansion of the nucleon-nucleon interaction, I will never get a term here that will describe the two clusters, but they are very far separated and interact with a point Coulomb, right? You can imagine if you have helium-3 and alpha very far apart, they will interact with a point Coulomb, where you have here, Z of the alpha, which is 2, Z of the helium-3 is also 2, the E square, and the R is the separation between them, right? So this is the long-range interaction, which always will appear in reality. But if I treat my interactions in the harmonic oscillator expansion, that's what I'm doing, then I will never get this. So then what we do, we add that by hand here, and subtract that from this piece. So we are adding it and subtracting. so I need to have it here, so that will allow me to really construct the proper boundary, okay, the proper boundary conditions for these clusters when they are far apart, right? It allows me to use the Coulomb functions when the two clusters are separate. But at the same time, okay, but obviously when I add something, I have to subtract it. So I'm subtracting it from the nucleon interaction, but here, this piece, I treat in my harmonic oscillator expansion. So that means that also the subtraction is treated in harmonic oscillator expansion. But because I have the point Coulomb in this piece from the proton-proton interaction, this difference now becomes short range, and therefore, this kind of truncation in the harmonic oscillator expansion is actually legitimate. So I'm not doing some nasty, cheating here. So this can be done actually. So this is, I just want to point out that this is an important issue that one has to deal with in this type of, so as I say, I mean, this is exact, but the fact that now I need to add this Coulomb and subtract, so that's already an approximation, which is good as long as my expansion of this part in the harmonic oscillator basis is sufficiently large. I mean, I keep a lot of basis states. Okay, and so now I have these, these channel states which I erased here. But so this is this channel state, right? Where I have the target projectile orbital momentum between those two, and then I had this, this G. So now what I can do, I can expand my, so that was, I had a delta, Dirac delta, right? So now I can rewrite this Dirac delta, which depends only on the absolute values of the coordinates, using the radial harmonic oscillator wave functions. Yeah. So this is again a mathematical identity, but the n here, the sum over the n, should go from 0 to infinity, right? So that obviously I will not do. However, I can do this as long as I do it only for localized parts of the kernels, right? So in the end, I want to calculate these kernels here with this expansion. And so now what I'm saying is I could use this expansion in the radial harmonic oscillators if the expansion is if it is done for localized parts of the kernels. And so why I want to do this? I'm doing that because with this kind of channel, I'm getting something very similar to what I have in my no-Korshel model expansion, where I used harmonic oscillator states. Yeah. So this is very advantageous because now I'm getting back to my harmonic oscillator expansion. But I stress that this expansion is done only for parts of these kernels. Yeah. So we cannot do it for. So we have to allow the system to separate to infinity for at least part of these kernels. So maybe I can show it more explicitly. So here I have an example of this object, this kernel here, and I consider the simplest case. So here I discussed the beryllium-7, helium-4 plus helium-3, but in this case let's consider even simpler case where I have only the projectile is a single nucleon. So that would be, let's say, like the proton helium-6, or in this case I can have neutron helium-4 or something like that, right? So this is what I need to calculate. And now these are the antisymmetrizers, which antisymmetrize this nucleon with those 4 nucleons there in the target. And so one can show that this product is just this, is 1 minus sum over from 1 to a minus 1 of the transpositions of single nucleons. So I have to, I exchange this nucleon, which I denote like with the index A, and one of those 4. Yeah, so this is what I need to compute to get this so-called norm kernel. And so now when I would do that, I will have 2 contributions. First, I have this 1 here, Yeah, and so the one is just a Kronecker delta and a Dirac delta. Yeah, so this is really like, again, nothing happens. So this is what I get. But this delta I am not allowed to expand with my radial harmonic oscillators, right? That's not legitimate. So this is what I was saying here. So I cannot do that for that part, because that part, is not truncated in any way. And this is really not some localized part. This could go, this could describe the system when they can separate all the way to infinity. But this second part, where I have the exchange of the nucleon with one of the nucleons inside the nucleus, that is localized, because the wave function of this, let's say helium-4, doesn't go, the wave function is localized in the space. So this matrix, for this kind of matrix element, for this exchange, I can use this trick of the expanding of delta with the radial harmonic oscillators, right? So I can do that. And so that's what we do in this, in this business of the no-Korshal model with continuum. Yeah. So in the end of the day, to calculate this norm kernel, again, I have just the plane delta, and then I have this part which describes the exchange, and that exchange I am expanding in terms of harmonic oscillators. Yeah. And as I say, this is legitimate because this matrix element is not, is really localized, because the wave function of this target is localized, and I'm exchanging a nucleon with one of those inside. And so now the task is to calculate this matrix element. So I will not go through it how it is done, but I will just say a few words about that. So I emphasized in the previous lectures in the no-Korshal model. In the no-Korshal model, we can calculate in Jacobi coordinates, but we can also calculate the Slater determinants, or its equivalent. And the Slater determinants are advantages if you have more than 4 nucleons. And so now you can imagine that I want to apply this theory to more than 4 nucleons, so therefore I better use Slater determinants. And so I do that, I can do that actually in these type of calculations for targets which have, so what I do is I will treat the target, in this case helium-4 or, lithium-6 or whatever, I will treat in a no-Korshal model calculations with the Slater determinant expansion. While the projectile, in this case helium-3, that I will calculate in the Jacobi basis. And now, if I calculate, if I have this wave function in Slater determinants, one can show, it's a little bit technical, and I will not go, I have it on the slides, but I will not go through that. So it's a technical thing, but the fact is that to calculate this matrix element, you actually get that from so-called one-body density of your wave function. So in this case here I will have, let's say this helium-4, so this will be a helium-4 expanded in Slater determinants, and I need to calculate A dagger A, which is the the creation and annihilation operator in my harmonic oscillator basis, acting on these wave functions eigenstates, that I compute that I compute in the no-Korshal model. So my statement is that this matrix element I can get from these, and those are easy to calculate. Now the question is, how you really relate them, but that's, I have it on the slides, but I will not go through it. Now, so that was, let's say, the simplest part was the calculation of this norm kernel, right? So I just sketched that. Now we also need to calculate this Hamiltonian kernel if I add the H there. So again, for this case where I have a single nucleon projectile, it is the H acting on this transposition, 1 minus the transpositions. So now this becomes more complicated. I will not, talk about it in more details, but just want to point out again. So I have, some part which is, just goes with this one here. and that's this first part. And the second part, which includes this transposition, and that then will give me matrix elements of the potential, of the potential energy, and then you get, you know, somewhat complicated things, and you can diagrammatically show that in the following way. So this, for this, you know, these potential kernels, you get a part which is called direct, where you have an interaction between your projectile and one of the nucleons in the target. Then you have to also take into account the antisymmetrization. That means that you exchange your projectile with one of the nucleons in the target, and then they would interact. So that is this first part. But then you have also a process where you would exchange the projectile with one of the nucleons in the target, and that nucleon will then interact with another nucleon in the target. And so this we call exchange potential. So it already involves two nucleons in the target. So actually it depends on the two body density of the target, while this process depends only on the body density of the target. So again, so this is more technical. I don't want to bother you too much with this. Okay. Yeah, so maybe just, so there are some pictures that should kind of give you a feeling what these kernels are all about. So these are pictures that Sofia Quaglione made a long time ago, but they are very nice. So this is our kernel, the norm kernel, and this is the Hamiltonian kernel. Yeah, and so the norm kernel, again, you know, it includes this exchange and then this direct part. And so I will focus on this exchange. So this is like trivial, so I don't have to bother. And so now, if I have helium-4 plus a neutron in the S wave, and you calculate this object, this is what you get in the, so this is the R, it depends on the relative distance between the neutron and helium-4. So I have the coordinate R and R prime. So this is a non-local object, right? So this is what I have here. So we have R and R prime, and what I'm calculating is, you know, just this. So I have one there, right? So this is R, R prime, so that's what I have, although I have the absolute values of R and R prime. And you see, this thing is actually negative, so it goes, you know, it's negative, while this is 1. So it's like you are summing 1 minus something negative in this S wave. And now if you look at this, this is the potential. So now I calculate the potential with this. So now I put here V. Yeah. And so here I have this, what I call a direct part of the potential, and this is the exchange part of the potential. So obviously this is, again, Pauli principle. I'm exchanging nucleons. And what you see now in this S wave, now this part is negative. This is a very large negative potential, so it's attractive, while this part is repulsive. Yeah. And so if you sum it up, it cancels to a large extent. And this also cancels, so this will give you some very small contribution of this norm kernel. So why is that? So this is because now what you are doing here is it's like you want to put your third neutron into the S state. So, you know, in this n equals 0 shell, you can have at most 2 neutrons and 2 protons. Yeah, and the wave function of the helium-4 in the ground state is mostly made of these, you know, this configuration where you have 4 nucleons in n equals 0. And so now in this, when I'm calculating this with the S wave, I'm trying to really put the fifth there. And so that's not allowed. And so that in this theory, you know, the manifestation that is not allowed is that this term cancels that term. And in the potential, this term cancels that term. So basically, you know, this will give you 0 in the end of the day. So you will not have that. On the other hand, if I use P waves, then it's completely different. So this is very small. You can see, I mean, the scale change. So this is like 0.0. And this has both the same sign. So these add up. So these will give you a strong attractive potential. And that allows you to get your ground state of helium-5 in this 3½ minus, you know, P3½ state. Yeah, so this is just a pictorial representation of these, you know, these potentials and this kernel that we get from this type of calculation. And immediately from these pictures, we already see, you know, what the physics is. So I think why don't we have a 5-minute break, and then I will continue. I have to stop at 1. So, okay, so let's have a break. Okay, so let me continue, because we have to end precisely at 1 today, so that we can have the excursion to the villa. Okay, so I discussed all this business with the non-core with continuum, and especially how to calculate these kernels. I have examples of these integration kernels that appear in this kind of theory. And so now I realize this is very technical. I have many slides on the details how to calculate these kernels, but I will not discuss them because that would be too heavy. If anybody is interested, then obviously you can look at the slides you can download, and also we have papers that describe that. And I think what I want, okay, so maybe just, I just will make a few points. So I said that advantage of the no-core shell model is that I can do calculations in Jacobi basis or in the Slater-determinant basis. And I take advantage of it also in this extension of the approach to continuum. And so when I have my cluster states, right, where I have this target projectile coupled to channel spin, coupled with the relative orbital motion with a total J, and then I have the relative radial wave function, which I also expand in the harmonic oscillators, but only for the parts which are localized. Then what I can do, I can actually substitute this or calculate this target wave function, which is the heavier one, using the Slater determinant expansion. Yeah, because let's say if I wanted to do lithium-6 on proton, then I would never be able to calculate lithium-6 in Jacobi coordinates. So I can conveniently calculate it with Slater determinants, and you can also do it if you use this big stick code, as I said before, and we can do it also in the afternoon. So anyway, so I can calculate this type of wave function in Slater determinants. And so now my statement is that if I do that, I can still recover my original cluster state, which is fully described in Jacobi basis. In Jacobi, this fully translation invariant. So for the reactions, it's really important that we have the system which is translation invariant, because the scattering that we do, let's say helium-4, helium-3, the scattering is done in the relative motion between those two clusters, right? So we need to have this coordinate, which is, as I said, I erased it, and it's the distance between the center of masses of those two clusters. And so it's critical that I have this kind of coordinate in my expansion, right? But then if I switch to Slater determinants, I don't have it. I can, if I have the Slater determinants, I introduce some new channel states that I describe here, where I have, this is the Slater determinant, this is in Jacobi, but now this motion would be in the, this coordinate here is the, the coordinate of the projectile, but not relative to the target, but relative, this is measured from some origin, right? Let's say I have I have my potential, so it's from the origin of the potential, not from the center of mass of this thing, what I want. However, now I take the advantage of the fact that my no-core shell model Slater determinant wave function eigenstate exactly factorizes as the Jacobi coordinate eigenstate times the center of mass in the 0 h bar omega motion. So this is, again, if I do no approximations, I do my calculations with the Nmax expansion, this is mathematically exact. And now I can take advantage of the properties of harmonic oscillators that I described here already at least 2 occasions. That is, I can write products of two harmonic oscillator wave functions as a linear combination of products of two different harmonic oscillator expansions. In one case, they will depend on these coordinates measured from some origin, and in the other case, they will be the proper relative coordinates, the one which I'm really interested in, between the center of masses of the reacting nuclei. And this psi 0 is just the center of mass of the whole system, which is completely irrelevant, right? I don't care about the center of mass of the whole system because that could do anything. I'm interested in the intrinsic motion, especially in the relative motion between those two clusters. So now, with this kind of expansion, this kind of trick, I am able to go from this basis, which I can construct easily, to the basis that I really care about, which is this one. So again, I will not go into further details, but this is, this is the second trick that we use in this NCSMC. So the first trick was to use this, this RGM Dirac delta expansion in terms of harmonic oscillators. Yeah, okay. So just again, so this is only done for these localized parts of the kernels. And then it's legitimate to expand in harmonic oscillator. And so we use the same type of expansion as for the eigenstates. So if I have eigenstates 10 h bar omega, I do this also up to 10 h bar omega. And then obviously you can, change to 12 h bar omega or to 8 and see what happens, right? So that's what we do. But again, I stress that there are terms in the kernels which are treated properly without any truncation. Okay, so now I have a slide, how to actually do it. So there's a transformation, but let me just skip that. But if you are interested, then you can look it up. So this is an exact. Again, you have this motion, this generalized harmonic oscillator bracket coming from what I had on the previous slide, and some recoupling, and from that you can get exactly what you want, and then you have some transformation that really allows you to completely remove the center of mass contribution from these later determinant eigenstates. Okay, and then and the point is, as I said before, I can relate. Now, if I have these later determinant eigenstates, I can compute my kernels using the simple objects like the densities that I can get from the wave functions very easily. So this A dagger A is like a one-Boy density of the target wave function, and that is easy to calculate in the no-core shell model or in the shell model. And actually, in this big stick code, there is an option for it. So if you want, you can just tell it, calculate one-Boy density, and it will do it. So it will give you these numbers actually, just directly from from the input. So, and if you have these numbers, you can calculate this kernels, and then you can plug it back to this formula I had on the previous slide to get really the translation invariant kernel. Okay. And then, okay, I also have to calculate the cross kernels, but that's kind of easier than these RGM kernels, but let me not go into that. But what I want to do as the last thing today would be to tell you how we solve the final equation that we get from this business. So so far I kind of was describing how to get these integration kernels, right? So this is very technically challenging, and is the hardest part. Okay, obviously it's very hard to get the wave functions in the first place, and the next complicated thing is to get these integration kernels. Once we have that, in the end, what we are getting is something like a Schrödinger equation. So it is a generalized, so I said, right, you have a generalized eigenvalue problem. So you have, this H psi, and you have some E n psi, right? So this is a generalized eigenvalue problems because you have this norm kernel which is not one, right? It's not because these objects are not orthonormal. So that's why you have the n. But now, so it's okay, it's not like a Schrödinger equation, but you can still solve it. It's not a problem. But maybe you don't like it. You don't like to have this kind of generalized eigenvalue problem. So what we can do, so we can just simply calculate n to the minus 1/2, right? And orthonormalize it. Yeah. So this is straightforward. So how you calculate n to the minus 1/2? So you diagonalize the n. Yeah. If you diagonalize, you get all eigenvalues, and you take the square roots of the eigenvalues and sandwich them with the eigenvectors, and you get the square root of n. And so now what I can do, I can redefine my basis. I can multiply this with n to the minus 1/2. This will be also, so here I will get n to the plus 1/2. Here I will get n to the plus 1/2 and n to the minus 1/2. Okay, so I will just put here n to the here I put 1, so n to the minus 1/2 times n to the plus 1/2, and here I have n minus 1/2 from the left, and so here I will have n to the plus 1/2. So now these will be new kind of eigenstates, right? And in the end of the day, I have something like n to the minus 1/2 h, n to the minus 1/2. And then I have some new state, and which is now in a form which is like a regular Schrödinger equation. Yeah. So this is straightforward. Again, I mean, this object I can get just by direct diagonalization of the norm kernel. And so then in the end, what you have is an equation with these unknown, let's say, relative motion wave functions. And you can actually rewrite it in this type of form. So as I said, very hard part is to calculate the n and then this h kernel. So this is integration kernel here. But once you have it, then you have something which very much looks like your regular potential scattering, right? So what is the difference? So r is the coordinate which describes the motion between the clusters. And so the only complication, compared to some kind of standard potential scattering is that here I have obviously coupled channels. I have many channels, and this is some non-local interaction, right? So if it was just depending on r, it will be local, but it depends also on the r and on r prime. So it's basically a coupled channel integral differential equation that I need to solve. But actually this is pretty straightforward, and it's again you can get equations like this in scattering theory, right? It's not just Korshal model with continuum. You can have many other theories. And so now before the lunch, I would like to describe or show you how to solve this, because I think it's of more general interest to solve this. Or let's say to describe the method that we call microscopic R matrix or Lagrange mesh. It's a very powerful method, and it could be used in more general. And then tomorrow I will just give the examples of applications. So tomorrow I will do no derivations whatsoever, just show you some results. I think I will show this helium-3 alpha gamma, because that was also discussed in the talk on the astrophysics by Gabriel, right? Okay, so maybe why don't we try to solve the scattering equations? And so maybe I can just do a simple thing. So let me just do the very I don't have to go through this equation that I had on the previous slide. It's the same. So we can just focus on a much simpler case of potential scattering, where you have a kinetic term, you have a potential and the energy, right? And U is your solution. And so now how to do it? Okay, so let's say I have my kinetic term part. Then I have the potential. I have the energy. And I have my wave function. Let's call it u r, and this is equal to 0. Okay, so this is what I want to calculate. And so now this would be a kinetic term. So that's what I denote that the TLR, and then I have the potential. So okay, so it's just this, and so it acts on, let's call it ULR, and that's equal to 0. Okay, and so now if I have no Coulomb in the if there is no Coulomb in the potential, so then asymptotically the ULR for R going to infinity, right, is just given by the incoming and outgoing spherical wave. So I will have, something like I half, and then there is e to the minus I k r minus L pi half. So this will be the spherical incoming wave, and then there is the scattering matrix SL. Okay, this is a single channel, so it's just your phase shift basically, and then you have your outgoing wave, right? And the SL is just nothing else than, so it's the scattering matrix, so it's nothing else as 2I delta L, okay? And so this, okay, and now if you have Coulomb, then instead of this simple relation, you will have incoming and outgoing Coulomb functions. So that then for a Coulomb it will have a more complicated form, and I will not go into more details of that, so it depends on the KR. Okay, so this is I half, and so now these functions, this h minus, that would be your incoming Coulomb function minus s. Okay, sorry. Yeah, so the h minus is the incoming Coulomb function, and the h plus would be the outgoing Coulomb function. But for the purpose of what I want to show, it's not really important to discuss the details of these Coulomb functions. We have a regular and irregular Coulomb function that you combine together to get these h functions. But even if we just focus on the simplest case without the Coulomb, the point is the same. So what we want to do here is to use something that we call the microscopic R matrix. So what we do is we introduce a matching radius. That means we divide our space in the coordinate, in the configuration space, using with some distance a, that has the property that the nucleon-nucleon interaction, or the interaction between the interacting clusters, will be 0 beyond this radius, right? And so now the only interaction that will be left beyond this radius is the Coulomb interaction, or if that is, if it's just a neutron, then obviously that will be 0, right? So it will be just a free system. But in general, this will be a Coulomb interaction here, while inside you have both the nuclear and the Coulomb together. And so now we know what is the solution in this part, and that is given by this asymptotic wave function. So that's what I try to write here. So when we go to very large distances where the two objects do not interact otherwise than with Coulomb, we will get either this kind of free or the equation or the one with the Coulomb functions. Okay, so I think this is obvious. But now, so what we do here in this formalism of what we call a microscopic R matrix on a Lagrange mesh, we introduce a basis, a special basis, to expand this wave function ULR in this internal region. So I have the internal region that goes up to the radius A. Yeah, so I will expand it with some, so I have a total number of n functions. So now the n is not radial harmonic oscillator wave function. This is has nothing to do with harmonic oscillators, right? So I have some expansion coefficients, which depend on the distance, right? And so now we make a very special choice of these functions, and so those are called Lagrange basis functions, and they are defined. Okay, they are basically defined by this equation here. So they they correspond to so they are related to Legendre polynomials. They are defined on this interval from 0 to A, and with this kind of prescription they have very special property. So this, if we use these functions, then this expansion is used in approximation of integrals. So this is used in the Gauss-Legendre quadrature. So if you have an integral of some function, which you would integrate from 0 to 1, you can write it as a sum of some weights and the values of the integral at some particular points, and those particular points will be exactly the points for this that satisfies this equation. Yeah. And these coefficients lambda can be obtained from this solution. So it is a very special functions that will be 0 at all mesh points except one. Yeah. So you can see that now if I go to these points xn, which are used exactly in the approximation of this integral, then there will be delta nn prime. So basically for all n's except one, this function is 0. So does it mean that if I would use this as a basis function, I get a very simple integral? So that is shown here. So if I use this fn as my basis function, then the integral of the, let's say, matrix element of the potential with this basis functions, which is an integral fn r vr fn prime r. So now you plug in this delta nn prime. What you get is just the value of the potential at the mesh point and the delta nn prime. So it cannot get any simpler, right? So this is, again, this kind of magical basis related to the Gauss-Legendre quadrature approximation of the integral that one can construct. And if we use this basis, then all the integrals that we have for the matrix elements of the potential, and now if I have, with this basis, let's say if I want to calculate matrix element of a non-local interaction, right? So I have, in my case, I will have non-local interaction. So from that you have two integrals to calculate, right? And so what you get in the end is just again, like in this case, for the simple, I mean the local potential, I will just have the same kind of expression. Yeah, so instead of doing two-dimensional integral, I only need a value of the potential at this mesh points. Yeah, so that's the magic of this particular choice of the basis. Yeah, and you always integrate only inside your on this region where you match, right? Yeah, okay. Do I have it somewhere? No, I think you are obviously right. I was just writing it, from the top of my head. But yeah, so you have weights when you do the integrals, right? So you have the weight, so that there should be one weight. Maybe lambda n prime. Okay, so this is approximate. Okay. Okay, but then, so that was one thing of this. You use this nice basis to expand. And so what you want to do next? So you know what is the solution at this site, right? This will be just the incoming and outgoing Coulomb function, or say it could be the spherical Bessel function and spherical Neumann function if there is no Coulomb interaction. And so now you need to match the wave functions at this radius. So internal part is expanded with these magical Lagrange mesh functions, and this side is expanded in Coulomb functions. And so now we need to match, and we need to match not only the values but also the derivative. So we can say we need to match the logarithmic derivative, and that is actually facilitated by introducing this so-called block operator, which acts exactly on the boundary. So you have a delta r minus a, so it's non-zero only at the boundary, and it involves a derivative with respect to r, which guarantees that the matching with the logarithmic derivative. So what I will do is now I will rewrite my equation that I have here, t plus v minus e. So I can rewrite that in a way that I would add this block operator that helps me to match the wave function. So I can rewrite that in so let's call it L. Okay, so I add it to the left-hand side and to the right-hand side of the equation. But now what I will do, I will treat these two asymmetrically and use, on the right-hand side, when I have the L on the right-hand side, I will use this expansion that depends on the Coulomb functions. And on the left-hand side, I will use expansion in terms of the internal wave functions with these Lagrange functions, right? And so then, if you do that, you will get a set of equations that I have shown here. So first you introduce this kind of C, what is called a C n prime n matrix, which is just the, let's say the matrix of the TL plus L plus V, and that's it. So this is what I call the C matrix, which is given again. These are these Lagrange mesh functions. So this is straightforward to compute. So the potential I showed you is just the value of the potential at this And now the kinetic term plus L can also be calculated in an analytic way. And actually, the meaning of this L is that when you add that, you will get a Hermitian kinetic term, or let's say that this whole object will be Hermitian on this, in this region from 0 to A. Yeah, so that Hermitize is basically the kinetic term. And then on the right-hand side, so that would be this part. And on the right-hand side, I will apply this block operator to these functions, and that will give me some derivatives of these functions. Yeah. And so now this method is called microscopic R matrix, and that is because we introduce this R function that is obtained by, you invert your C minus E, and then you sandwich that with these Lagrange functions, but now calculated at the boundary. Yeah. So I gave you the expression for this f function, right? So it's a little bit complicated, depends on this Legendre polynomial, and it's very simple if you put R to set R to xn, for which the p to xn minus 1 is 0. But you can also plug it for the R equal A, and then you will get something else. And I don't have the expression here for that, but it's obviously not so complicated. And from that you can construct this R matrix, and basically now using that you can compute your S matrix. So the whole point is that now from this, the S matrix is hidden here, right? So it's multiplies the outgoing waves. And so by introducing this R matrix, you can then calculate your S matrix or the phase shift in this compact form. So the whole thing can be generalized for the coupled channels. So I will not go through that. I have 4 minutes. So I have slides for that, so you can easily, so my equation was a little bit more complicated. So I have this non-local interaction, and I have coupled channels. So there are many channels. What I have done here was just for a single channel, like a potential scattering. So you can do the same thing now for the coupled channels. Then the C matrix is a little bit more complicated. And here you have this matrix element of the non-local interaction. But in the end of the day, again, is the just the C minus E inverted, and the F ends on the boundary, and from that you get your S matrix now in a more complicated way. But in any case, that's straightforward algebra. So this is a very powerful method that we use to solve these no-Korsham continuum equations, but it's used in any other problem that wants to solve the scattering equations, or so I think it's useful to be familiar with it and try it. And the main advantage is that you really don't have to calculate the integrals, because you rely on this Gauss-Laguerre quadrature with these basis functions, and then all the integrals collapse to just values at the mesh points. Yeah. So that makes it very efficient, especially if you have coupled channels. If you would use some other method, it will be definitely much more numerically complicated. So maybe I just want to say how, let's say when we do this, we don't, you don't need that many mesh points to solve this. So in the no-Korsham model with continuum, when we solve this, right, so these are the equations, or yeah, so this is my equation. So when we solve it, so typically we would use A, something like 15 Fermi. So that is well beyond, so the nuclear interaction range is I don't know, 5 Fermi or not more. So we would use something like 15 Fermi, and the number of the mesh points, so this capital N here, so that if we use 30 or 40 or maybe can use even if you use 80, but okay, it's still not that many. So that's a very easy to do the calculation with this. So it's very fast. Even if you have many couple channels, you can imagine that if you have some more complicated problem, then the number of these channels C, it could be tens or even more. So it's in the end, it's a very large matrix. And now, if you would do it some other way, and you will discretize, your coordinates somehow, then you may need not 30 or 40 points, but maybe 1,000 points. So it will be much, 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 much bigger. So this is an extremely efficient method, and so it was developed by large extent actually in Brussels by advisor of Jeremy, by Daniel Bay, and it's very, very useful method. Okay, so I think I will stop here, and then tomorrow I will just show you some examples of the applications of this, and especially I would focus on the reactions that are useful for nuclear astrophysics. Okay, thanks.